Okay, last lecture we dealt with carboxylic acids, and this lecture we're going to deal with carboxylic acid derivatives. Carboxylic acid derivatives are going to be given in two videos. The first one will deal with the general formula of the carboxylic acid derivatives, their nomenclature, and their synthesis. The second part is going to deal with their reactions and their specific reactions, the general reactions and the specific reactions, together with the active methylene compounds. Okay, first of all, when we started talking about carboxylic acids, we said that carboxylic acids include a carbonyl moiety and an OH. And that's why we said that they are bifunctional. We have the carbonyl as one functional group and the hydroxy as the other functional group. Carboxylic acid derivatives are exactly the same as carboxylic acids, but we remove the OH and we add another group in its place. This group is sometimes halogens, and these are the acid halides. If they are another acid, carboxylic acid moiety, then these are the anhydrides. If they are an alcohol moiety, these are the esters. And finally, if we have an amine group, then these are the amides. Okay, these are the different acid derivatives that we will deal with, and this is how we mention them in this order, because this is their order of reactivity. We say first acid halides, anhydrides, esters, and finally amides. We mention them in this order so that we can always remember their order of reactivity. As we said, acid derivatives are the acid halides, anhydrides, esters, and amides, and we saw how these compounds are drawn, what are the functional groups that are available in these groups. First of all, we will deal with their nomenclature. As we mentioned, whenever you are giving an EUPAC nomenclature, you usually go back to the original name. You look for the longest chain containing the highest priority functional group, and you go back to the name of this of this long chain, the longest chain, you go back to its name. In case of acid derivatives, you have already named the acid. You do not have to go back to the alkane. You have already named the acid. And how did you name the acid? You looked for the longest chain containing the carboxylic group, say for example something like that, and this contains 1, 2, 3, 4, so this is a butane, and then you remove the E and you add it OIC, butanoic acid. Starting from this point, we will start naming the different acid derivatives. In case of acid halides, you will take the name of the acid itself, and you will remove the IC and you will put IL in their place, and then the name of the halogen. So this is butanyl halide. Okay. In case of anhydrides, you will take the name of the acid. Say for example you are dealing with acetic acid or ethanoic acid. You will take the name as a whole part. You will not remove any parts from the name of the acid. You will only remove the word acid, and then you will add the word anhydride. So in case of acid halides, you remove the IC and you added IL and the name of the halogen. In case of acid anhydrides, you remove the word acid and you added the word anhydride. In case of esters, you always have two parts. You have an acid part and an alcohol part. Okay, which part is the acid? How can you recognize the acid part and the alcohol part? The alcohol part is the part attached to the oxygen. The one attached to the oxygen, the alkyl group attached to the oxygen, this is the alcohol part. And the part attached to the carbonyl is the acid part. And don't remember to count the carbonyl with the acid part to decide how many carbons you have in the acid part. Okay, how do we name it? First of all, we write the name of the alcohol. This is an alcohol having one carbon atom, so this is the methyl alcohol, so we say methyl, and we leave an empty space. We do not add anything in this empty space. No dashes, no commas, no points, no brackets, nothing. You have to leave an empty space. And then you add the name of the acid. This is acetic acid, so this is acetic. I remove the IC and add 8. So this is methyl acetate. Suppose that I'm using the name of the acid part in the form of the EU pack, not acetate. I'm not going to use the word acetic acid. I'm going to use the word ethanoic acid. So this is ethanoic. I will remove the IC and add the 8. So this is methyl ethanoate. Let's look at another example. If we have, for example, the benzoic acid forming an ester with ethanol, for example. So now the alcohol part is the part attached to the oxygen. This contains 2 carbons, so this is the ethyl alcohol. And then we leave an empty space, and then we have the acid part attached to the carbonyl, and this is benzoic acid. We will remove the IC and add the 8. So this is ethyl benzoate. So remember, in case of the acid halides and in case of the esters, you removed the IC only and added your part. In case of the halides, you added an I. In case of the esters, you added an 8. Okay, this is in case of the acid halides and the esters. In case of anhydrides, you removed nothing except for the word acid. Let's go to the amide. This is the only exception. In case of the amide, you will remove the whole OIC. So this is, for example, acetic acid. You will remove the IC and you will add the word amide. So this is acetamide. Let's look for its EU pack name. This was ethanoic acid. So you remove the OIC. It's going to be the ethanamide, the whole OIC. In case of acid halides and esters, you left the O. You removed only the IC and you left the O. You didn't remove the O. In case of amides, you remove the whole OIC and you add the word amide. Okay? Remember this. This is your only exception. Okay, we have a class that is very close and very similar to amides with slight differences, and this is the emides. What are emides? Emides are amides that are attached to another carbonyl. You have the amide, nitrogen, having another carbonyl as a substituent on it. This is called emide. How do we name it? We name it exactly the same as amides. Say, for example, this was acetic acid. So this is acetic acid. You remove the etic and you say acetamide. If it was phthalic acid, for example, so this is phthalic acid, you will remove the IC and you will say this is phthalimide. Why do we focus on emides? Because emides are highly characteristic. Why is that? Because if we first deal with amines, we consider amines as basic compounds, and I'm going to explain the nitrogenous compounds within 2 or 3 lectures, and I will tell you why are amines basic compounds. Amines are basic compounds because they contain a lone pair of electrons on the nitrogen that are capable of accepting a proton. Okay, so this is why they are bases. Bases are compounds that can accept protons. So amines are basic compounds. If we consider amides, amides are not basic compounds. Why is that? Because the lone pair of electrons of the nitrogen are involved in a resonance with the carbonyl compound, with the carbonyl group. So they are neutral compounds. They are not basic. If you test their basicity, you will find that they are not basic. However, emides are not basic and they are not neutral. They are acidic. Why is that? Because if you remove this hydrogen and you leave a negative charge in its place, this negative charge will be stabilized by two resonance and not just one. It has two carbonyls attached to it. So this is high stabilization, and that's why this proton is easily lost as a proton, leaving a negative charge on the nitrogen. These compounds are acidic compounds, and when you test for phthalimide in the lab, you can see slight effervescence with sodium carbonate. It's true, it's a very weak effervescence, but still it's present and you can see it. So these compounds, imides, are weakly acidic compounds, and this is due to the resonance between the negative charge on the nitrogen left after the hydrogen leaves as a proton and the two carbonyl groups. So this is imides. One last thing for the nomenclature before we end it. If we look at amides, as we said, say for example you're dealing with acetamide and you added a methyl group attached to the nitrogen of the amide. So as we mentioned before, this is the acid, so this is acetic acid. I will remove the IC and add the word amide, so this is acetamide. How do I mention the substituents on the nitrogen? These substituents will not carry numbers for their position. They carry N. We say N-methyl. If you used a number for these substituents, then the substituent is not on the nitrogen, it's on the acid part. The acid part is the part that takes numbers for its substituents, while the nitrogen part takes N for its substituents. Suppose we have two substituents and not just one. For example, two methyls. So this is which acid? This is benzoic acid. You will remove the OIC, so this is benzamide, and then you will say N-dimethyl, benzamide. Suppose that one is a methyl and one is an ethyl, so this will be the N-ethyl, N-methyl, and then the word benzamide. As I mentioned, if you use any numbers for this compound, for these compounds, for the amides, you are actually substituting the acid part, not the amine part. The amine part takes an N. Your substituents are lying on a nitrogen, so they are N substituents. They are not on the acid. If we go through these, if we go through this part, the nomenclature of acid derivatives quickly on the arranged, the well-organized slides, we will again see that in case of acid halides, you will remove the IC and you will add the IL and the name of the halogen. In case of anhydrides, you just remove the word acid and you add the word anhydride. In case of esters, you will put first the alcohol part, you will leave an empty space, and then you will put the acid name, removing only the IC as we mentioned and adding an 8 in its place. So this is ethyl acetate or ethyl ethanoate. Again, this is benzoic acid and ethyl alcohol, so this is ethyl benzoate. In case of amides, as we said, you will remove the whole OIC. If there's no IC and OIC and there's only an IC, then remove the IC. However, if there exists an O in the name, there's an oic part, you will remove the whole oic part and you will add the word amide in its place. Okay, as we mentioned, if you have a substituents on the nitrogen, on the amine part, it will take an N for its position. If there's more than one substituent, then you will repeat the N. As we mentioned, there is a class that is highly close, or very close and similar to the amides, and this is the imides. These are amides, but having another carbonyl as a substituent. As we mentioned, they are exactly named as amides. You will remove the IC or the OIC from the acid, and you will add the word imide in its place. And as we mentioned, these are highly acidic, these are weakly acidic compounds. Their acidity comes from the fact that they can remove the hydrogen as a proton and leave a negative charge on this nitrogen that is stabilized to the both carbonyl compounds by resonance. Now we will talk about the synthesis of these compounds, but for the first time in all organic chemistry, first and last time in all organic chemistry, before we mention the synthesis of these compounds, we have to discuss their reactivity, because it plays an important role in deciding the starting material for each one of them. Let's first discuss the reactivity, not the reactions, just the reactivity, the order of reactivity of these groups, because as I said, it plays an important role in their order, in choosing their starting materials. We have, as we mentioned, a carbonyl group attached to a leaving group, which is halogens in case of the acid halides, another acid molecule in case of the anhydrides, an alcohol molecule in case of esters, and an amine in case of amides. So what reactions do we expect? Exactly the same as all carbonyl compounds. You have a partial positive on the carbon, so you are expecting a nucleophilic attack on this carbon. First of all, the carbonyl will break, the pi bond between the carbon and the oxygen will break, and then it will reform, allowing the leaving group to leave the molecule. So this is again a nucleophilic substitution reaction where you remove the Z, or you substitute the Z with your nucleophile. All this is possible due to the partial positive charge on the carbon of the carbonyl. So to arrange these compounds in and decide their order of reactivity, we have two factors. This reaction involved two steps. The first step was the attack of the nucleophile, the attack of your nucleophile on the carbonyl. This attack is governed, or is ruled, or is decided by the degree of positive charge on the carbonyl. The higher the degree, or the higher the positivity of this carbon, the better the reaction is. The lower the positivity on the carbon, the lower the reaction, or the lower the rate of this reaction. The nucleophile is looking for a positive charge. The more the positive charge on the carbon, the better for this reaction. The second part of the reaction is the leaving of the leaving group. The better leaving capability of this Z, the better the reaction. So we have two factors. Let's discuss the first factor, the positive charge on the carbonyl. Supposing that the R attached to the carbonyl is the same in case of all derivatives, we will have only one factor, which is the Z. Let's discuss the different Zs. In case of acid halides, the Z is a halogen. In case of anhydrides, the Z is an O and another acid. In case of esters, your Z is the alcohol part, and in case of amides, your Z is an amine. Let's discuss the effect of each one of these on your positivity of the carbonyl group. The halogen. What is the effect of the halogen on a carbonyl group? Is it a donating or a withdrawing group? It's a withdrawing group. By which mechanism? By induction. Remember that the positive resonance of the halogen is negligible. We do not deal with the positive resonance of the halogen. So we only have a negative induction. In case of acid anhydrides, we have an oxygen attached to the carbonyl. What is the effect of the oxygen? First of all, it's a highly electron withdrawing group by induction because it's more electronegative than the carbon, so it withdraws electrons by induction, but at the same time it has a lone pair of electrons that it can donate by resonance, so it has a plus resonance effect. However, it's not a full resonance. Why is that? Because the oxygen donates the lone pair of electrons by resonance to two carbonyls and not just one. Both carbonyls are within the same range of the oxygen. This oxygen can form resonance with this carbonyl and it can form resonance with this carbonyl. So only half of the time the lone pair of electrons are in resonance with one carbonyl and the other half it's with the other carbonyl. So that's why we say that it gives electrons by half resonance, not full resonance. In case of esters, again, you have the oxygen that is more electronegative than the carbon, so we have the negative inductive effect. And again, you have the lone pair of electrons that can be donated by resonance, but in this case, it's full resonance. The oxygen doesn't have neighboring to it except one carbonyl. It has only one carbonyl, so you do not have to do this. You do not have to add this half resonance. In the case of anhydrides, you had two carbonyls, so the resonance was only half the time with each one. However, in this case, we have only one carbonyl, so your resonance is only, the resonance from the oxygen is only towards one carbonyl, and thus it's a full resonance. In case of amides, again, you have a nitrogen that is highly electronegative, more electronegative than the carbon, so it performs a negative inductive effect. And again, it has a lone pair of electrons that it donates by resonance. Let's look at the derivatives, their order of reactivity, or the degree of the positive charge on each carbonyl in case of each derivative. In case of the acid halides, you have a withdrawal effect with no donation. So this is the most positive. We do not donate electrons to it by any means. The only factor is withdrawal. So this is the highest positivity of them all. So this is the most reactive. In case of anhydrides, you are withdrawing by one effect, which is the induction, but again, you're donating by half a resonance. Not full resonance, like in case of esters and amides, just half resonance. So this is less positive than the acid halide, but more positive than the ester and the amide. In case of esters and amides, we have both effects, negative induction and plus resonance, and negative induction and plus resonance. So we can consider both of these compounds having the same reactivity, but this is not true. They do not have the same reactivity. The esters are more reactive than the amides. Why is that? Because the positive charge on this carbonyl is more pronounced than the positive on the amide carbonyl. Because oxygen is more electronegative. Oxygen is more electronegative than nitrogen. So when it withdraws electron by induction, it withdraws more than the nitrogen because it's more electronegative. And when it donates by resonance, it's reluctant. It doesn't want to donate electrons by resonance. It's holding on. It's keeping its electrons. So it's not donating them that easily. And that's why esters are more reactive than amides. Why did we mention the reactivity of the acids at the beginning? Because the rule says that the less reactive can be synthesized from the more reactive and not the other way around, which means that you can use the acid halide to synthesize the anhydride, the ester, and the amide. And you can use the anhydride to synthesize the ester and the amide. And you can use the ester to synthesize the amide. However, you cannot use the amide to synthesize any of them because it's weaker in its order of reactivity. You can always prepare the less reactive from the more reactive and not the other way around. Okay, so this is the rule. Let's discuss the other factor that governs the reactivity of these compounds. As we said, we have two factors. The first factor was the positive charge on this carbonyl. The second factor was the leaving capability of the Z. The more the leaving capability of the group, the better the reaction. The leaving group will leave readily. It will not be reluctant. It will not say, yes, I want to leave. No, I don't want to leave. It will leave. It will be readily leaving. So the better the leaving group, the better the reaction. So let's discuss halogens versus acids versus alcohols and versus amines as leaving groups. Before we discuss this, we have first to remember few basic points. The first thing is that strong bases are bad leaving groups. Why is that? If a mighty is a strong base. What is the definition of a strong base? A strong base is a molecule that is actually looking for a proton in a desperate manner. It's really in high need of a proton. If I cannot stand by myself and I'm in a desperate need for a proton, I'm looking for it in whichever place. I'm willing to take a proton from anything. I don't care whether it's acidic or not. I'm going to abstract a proton from whatever mighty in front of me. This means that I am not stable as such. If I'm looking for a proton desperately, that means that I'm not stable. I need something to stabilize me. So if I'm not stable, then I'm not readily leaving. I'm not going to leave and be unstable. I'm already a part of a molecule and I'm stable. If I leave and I carry a charge and I become a base, if I am a strong base, then I am a bad leaving group. If I'm a weak base, that means that I'm okay. I don't need a proton that much. It's okay. If I can find a proton, it's gonna be perfect. I need a proton, but I don't need it that much. So that means that I'm stable by myself. I'm not desperate for someone to help me to stabilize myself. So strong bases are bad leaving groups, while weak bases are good leaving groups. So this is the first fact. The second fact says that basicity is inversely proportional to acidity, which means that a strong acid is a weak base and a weak acid is a strong base. So let's remember these points and then we will discuss the leaving capability of our group. So now if we look at halides, if we add a proton to halides, these become the inorganic acids, which is, for example, something like hydrochloric acid, hydrobromic acid, and so on. In case of the anhydrides, the other acid part, if we add a proton to it, this becomes a carboxylic acid, which is organic acid. So these are the organic acids. The alkoxide part of the ester as a leaving group, if we add a proton to it, this becomes the alcohol. And finally, the amine part, if we add a proton to it, it becomes the amines. Let's compare the acidity of these compounds first. It's well known that inorganic acids are much more stronger acids than carboxylic acids. It's a well-known fact that something like hydrochloric acid is much stronger than any of our organic acids. Organic acids are much weaker than inorganic acids. So these are more acidic. Again, if we compare the acidity of carboxylic acids with alcohols, as we all know, alcohols are neutral compounds. So carboxylic acids are more acidic than alcohols. Now, amines are basic compounds. If a compound is basic, then it's not acidic whatsoever. So the alcohols that are neutral are considered more acidic than basic compounds such as amines. This is the order of acidity. In this direction, acidity of these compounds decreases. Acidity of these compounds decreases. The hydrogen halides are the most acidic. So basicity will decrease in the other direction. Which means that if we discuss the other side, the leaving group itself, this is the least basic. Basicity decreased upwards, which means that the top is the least basic. So this is the least basic. The inorganic acids are less basic than the conjugate base of the inorganic acids, less basic than the carboxylic acids, less basic than the alkoxide parts, and less basic than the amine moieties. So these are the best leaving group, as we mentioned. Weak bases are the best leaving groups, while these are the strong bases, so these are the worst leaving groups. So order of reactivity of acids will be in this direction. These are the least basic compounds, so they are the best leaving groups, so they are the most reactive, which falls in consistency with the electronic factor. As you remember, acid halides, their carbonyl had the highest positive charge. So they have the best leaving group and they have the highest positive charge. Followed by the carboxylates, which are the anhydrides. They have a lower positive charge than acid halides and a less leaving capability. Followed by the alkoxides or the esters, followed by the amides leaving where their leaving group is the amines. As we mentioned, you have the acid halides, and then you have the anhydrides, you have the esters, and finally you have the amides. So as we said, this is the highest positive. So we have here 4 positive, only 3 here, 2 here, and 1 here. And this is the best leaving group, followed by this part, followed by this part, followed by this part. So now you have both factors are in the same direction. Both factors specify that the acid halides are more reactive than the anhydrides, more reactive than the esters, and more reactive than the amides. Okay, so as we mentioned, you can use the acid halides to synthesize any of these derivatives. And you can use the anhydrides to synthesize the esters. You can use the esters only to synthesize the amides, and you cannot use the amides to synthesize any of them. Let's discuss the synthesis now that we have mentioned, and we have already discussed the reactivity of these compounds. As we mentioned before, in case of the acid halides, you cannot actually synthesize them except from the acids. All the acid derivatives, all the other acid derivatives are less reactive than the acid halides, so you cannot synthesize acid halides from them. You can only synthesize them from acids using any halogenating agent. While in case of anhydrides, you can use the acid and the more reactive acid derivative, which is the acid halide. One other moiety that you can use is the salt. So you can use the acid itself, you can use the salt, and you can use the acid halide to synthesize the acid anhydride. In case of esters, you can again use the salt or the acid itself, or the two more reactive acid derivatives, which are the acid halides and the anhydrides. In case of the amides, you can use the acid itself, or you can use any of the more reactive acid derivatives, which are the acid halides, the anhydrides, and the esters. This is why we discuss the reactivity of these compounds before we discuss their synthesis, so that you don't have to memorize what starting materials are used for each one of them. The acid is common. In all of them, you can use the acid to synthesize them because it's the parent of these derivatives. In case of the anhydrides and the esters, you can use the salts. In case of each one of them, you can use the more reactive derivatives. Okay? One last thing we're going to discuss for this lecture, which is the physical characters of these compounds. In case of acids, as we mentioned before, acids can form dimers, and that's why their physical characters, including their solubility, their melting and boiling points, are high because they form dimers and they form hydrogen bonds with the water molecule, and that's why they are highly soluble and they have high melting and boiling points. In case of acid derivatives, now you have removed the OH and you have added a Z. This Z is a halogen, so you cannot actually form a hydrogen bonding. If it's an anhydride, so it's another acid molecule, you cannot form a hydrogen bonding. And if it's an alcohol, you cannot form a hydrogen bonding. For a hydrogen bonding, you need a hydrogen attached to a highly electronegative atom like oxygen, nitrogen, and sulfur. So if you don't have this moiety, you cannot form a hydrogen bonding. If you look at the acid halides, they do not have a hydrogen attached to an oxygen, nitrogen, or a sulfur. The same for the acid anhydrides and the same for the esters. So these compounds have lower solubility and lower melting and boiling point than the parent acids. However, in case of the amides, it's true you do not have a hydrogen attached to an oxygen, but you have a hydrogen attached to a nitrogen. Again, the nitrogen is a highly electronegative atom, so it will attract electrons, it will carry a partial negative charge, and the hydrogens will carry a partial positive charge, and it can form hydrogen bonding with water and can form hydrogen bonding with the other amide molecules. So amides are having the same solubility and melting and boiling point as the parent acid. When can amides lose this property? If they would be, if I remove the hydrogen and substitute the amide, nitrogen amide. If I remove the hydrogens on the nitrogen, for example, something like that, then I'm only capable of forming one hydrogen bond. Remember, the primary amide that was carrying no substituents on the nitrogen was capable of forming two hydrogen bonding, while the secondary amide, having only one hydrogen and an alkyl group, can form only one hydrogen bonding. The tertiary amide that is carrying two alkyl groups and no hydrogens on the nitrogen is carrying no hydrogen to form hydrogen bonds, and thus its melting and boiling point and its solubility is comparable to all the other acid derivatives because it forms no hydrogen bonding. Okay, so primary amides are comparable to acids in their physical characters. Secondary amides are comparable to alcohols in their physical characters, and tertiary amides and all the other acid derivatives are comparable to aldehydes and ketones in their physical characters. Okay, let's look at this last slide. So as we mentioned, carboxylic acids, they are polar, but they are not having high boiling or melting point and no high or boiling and no high solubility, because they are incapable of forming hydrogen bonding, whether with the water molecule or with other acid derivative molecules, except for amides. As we mentioned, they are capable of forming the hydrogen bonding with themselves, intramolecular hydrogen bonding with themselves, and intermolecular hydrogen bonding with water, so they have comparable physical characters to the acids. If we substitute one of the hydrogens with an alkyl group, we lose one of the hydrogen bonding, and we only have now one hydrogen bonding to another molecule of the acid amide or to water, and that's why they're comparable to alcohols. If we substitute both R's, then we do not have the option of hydrogen bonding and we become comparable to aldehydes and ketones.